Hi there. In this video I'll be answering a question on nuclear reactors, discussing the role of the control rods, calculating the power output of a reactor, and performing a half-life calculation. This is a question from the 2014 Intermediate 2 paper. A nuclear reactor in a submarine uses uranium fuel rods. During a chain reaction, uranium nuclei undergo nuclear fissions in the reactor. Part A then says the reactor is fitted with boron control rods. These can be lowered into the reactor. What effect does this have on the chain reaction? You must explain your answer. Now, as luck would have it, I actually know the answer to this one. Raising the boron control rods speeds up the chain reaction, making it more vigorous, and lowering them slows down the chain reaction. To explain why, we'll take a closer look at a fission reaction. I'm borrowing an animation from another one of my videos called National 5 Definition 6, Radiation. This is a neutron, and this is a uranium nucleus. The large uranium nucleus can be made to split when bombarded with a neutron. This is known as induced fission. In the fission reaction shown, two smaller nuclei are produced, together with 1, 2, 3 neutrons. Now, obviously in a nuclear reactor, there are millions and millions of reactions taking place at the same time. If each fission reaction requires 1 neutron to start, or induce it, but produces 3 neutrons, which themselves could cause further fission reactions, then very quickly the reaction would get out of hand. We call this an uncontrolled chain reaction. The job of the boron control rods is to absorb the excess neutrons produced in the fission reaction. Back to the question. Our answer then is that lowering the boron control rods slows down the chain reaction because they absorb neutrons. Now, just remember that if you're asked to explain your answer, then you should at least attempt one, even if you're not sure what the explanation is. In this question, writing the first part of the answer correctly, that lowering the boron control rods slows down the chain reaction, would get you no marks unless you at least attempt an explanation. On to part B now. The reactor produces 2.4 times 10 to the power of 9 joules of energy every minute. Calculate the power produced by the reactor. So of course the equation linking energy E, time T and power P is this one. Just remember to spend some time memorising the symbols for all the quantities in the relationship sheet. It'll make finding the right equation so much easier. We'll also need to convert time into seconds. So substituting our values into the equation, we get 2.4 times 10 to the power of 9 divided by 60, which is 4.0 times 10 to the power of 7 watts. At National 5 level, forgetting to convert time from minutes to seconds would cost you 2 out of 3 marks. So it's also important to remember the correct unit for each quantity. If you need help, then you can download a file called Help with a Relationship Sheet from my website. Part C of this Intermediate 2 question doesn't relate to National 5 physics, so we'll skip straight to Part D. Radioactive cesium is a waste product of the fission reaction. Cesium has a half-life of 30 years. Part 1 then says, a cesium sample was removed from the reactor on the 1st of January 1954. On the 1st of January 2014, the activity of the sample was 4 times 10 to the power of 12 becquerels. Calculate the activity of the sample on the 1st of January 1954. First off, you should know that the half-life of a radioactive sample is the time for its activity to decrease by half. Now, normally in a half-life question, we're given an initial activity, which we then have to halve several times to give us the final activity of the sample after a given time. Here though, we're told the activity in 2014 and asked to calculate the activity in 1954, 60 years previously. Let's start with the activity on the 1st of January 2014, 4 times 10 to the power of 12 becquerels. 30 years before this, in 1984, the activity would be double this value, 8 times 10 to the power of 12 becquerels. A great year 1984, Gremlins, Ghostbusters, The Karate Kid, Indiana Jones and the Temple of Doom. Ah, the good old days. Anyway, 30 years before this, and no, I'm not that old. In 1954, the activity would again be double. That means that the activity on the 1st of January 1954 would be 16 times 10 to the power of 12 becquerels, or 1.6 times 10 to the power of 13 becquerels. Finally, this is the last part of the question. D part 2 asks us to calculate how many nuclei would decay during a 5-minute period when the sample has an activity of 4 times 10 to the power of 12 becquerels. So the equation which links activity A, number of nuclei decaying n, and time t is this one. To make n, the number of nuclei decaying, the subject of the equation, multiply both sides by t. When we substitute activity and time into the equation, remember to convert time from minutes to seconds again. This gives us 4 times 10 to the power of 12 times 5 times 60, which is 1.2 times 10 to the power of 15 nuclei decayed in that time. I'm afraid that's us for another video. If this has been of any use, then please subscribe to stay updated when new videos come out. And if you've got time, check out those movies from 1984. For more information on upcoming videos, summary sheets and so on, visit physics-podcast.co.uk. Thank you for listening.